So far, we have discussed changes in velocity and speed, but have not discussed how these changes change. When talking about displacement, we have learnt how changing displacement with regard to time generates a velocity. When we change this velocity over time, we generate acceleration. The same is true for distance, speed, and acceleration. But what happens when we change acceleration? This does happen, but we don't have a term for it. It is very difficult to see, yet it happens all the time. When you're in a car and the driver puts their foot down on the fuel pedal, many things can be described as happening. All that really happens is that more fuel is added to the engine, and this generates more energy. The displacement or distance of the car is increased. This increase leads to an increase in the speed and velocity. This increase is called acceleration. But what happens if we leave the fuel pedal depressed? The fuel effect is cumulative. Not all of the energy from the fuel is transferred to acceleration. As the system gets warmer, more energy is transferred to motion, and so our acceleration changes. The rate at which we are getting faster gets faster. When we take our foot off the pedal, the acceleration decreases. Forces opposing motion do their job and slow down the car. These forces are proportional to the speed we are travelling. The faster the car goes, the greater the force is. So, as we slow down, the force applied to the car decreases. This means that acceleration is not constant, but changes. This is called non-uniform acceleration. We will describe it to a limited extent here, but it is in itself a field of advanced study in physics called nonlinear physics, or chaos theory. In a non-uniform acceleration, the acceleration is changing, and you must make your calculations of motion at given times. The motion properties derived from these equations at that point in time may not directly link to the equations at another point in time, as something has happened to affect the acceleration and therefore the whole motion system. We can represent non-uniform motion in our motion graphs. In a distance, displacement time graph, all the usual rules described previously apply, except the curvature is not smooth. The rate of curvature changes, and so makes the curve jagged. The overall pattern is still away from or towards the horizontal, but the smoothness is gone. For speed-velocity graphs, it is easier to see. For uniform acceleration, there would be a distinct change from one gradient to another. For non-uniform accelerations, this change is curved. A typical non-uniform acceleration is shown as a curved speed or velocity time graph, remembering that the rules for speed or velocity time graphs still apply. Here, however, the lines will curve to show non-uniform acceleration.